we call a subgraph of a graph any graph in which the vertices is a subset of the vertices of the original graph. So, for instance, given this graph that we have here, we can construct a subgraph by considering only, let's say, these three vertices, and the set of edges of my new graph have to be contained in the set of edges of the original graph, but with the extremes only in B prime. So, for instance, in this case, I can take an edge between these two. For instance, I couldn't take an edge between this because this edge was not in the original. So I can take, for instance, this, and if just this will make a graph. So my new graph will be, for instance, this one, a vertex between E and A, and the node B along there. That's one possibility of subgraph. Another one could be if I consider, for instance, this, and this. And so as edges, I have to get some subset of these ones, right? I can get them all or some subset of them. Let me take, for instance, just one here, and this. For instance, that would be another example of a subgraph of this one. And as a particular case of subgraph, it's going to be called spanning subgraph when the set of vertices is the whole thing. I mean, when it goes through all the vertices. So, for instance, this one is not going to be a spanning subgraph. This one is not going to be either. So, in order to be a spanning subgraph, I have to consider all the vertices of the original graph. The edges can be anything, but the vertices, in order to be spanning, have to be all the vertices. So, for instance, a spanning subgraph could be this vertex with this edge, with this one, with this edge, this one, and this one, and this one, and this, and this. That thing that I paint there in purple is a spanning subgraph because I'm going through all the vertices. And now, a very important concept in computer science is what is the spanning tree. And this is just a spanning subgraph, meaning a graph in which we consider all the vertices, but with this important property. This graph has to be a tree. So, for instance, this example that we had before, I mean, this lilac subgraph here was a spanning subgraph, but it's not a spanning tree because it has a cycle here, so the purple thing is not really a tree. So, let's try to find here in this graph a spanning tree. So the idea is to get a subgraph that spans the whole set of vertices, but at the same time is a tree. I mean, we don't put any cycle there. So you will start, for instance, any vertex here, and I go to here, and I go to here, and I go to here. But now I have to be careful. I cannot take this one, right? Because then I make a cycle there. Remember that we have to keep in mind the idea that should be a tree. So I can take this and this. That's a possibility. It's not unique, but you see that this graph that I mark in red is a tree. I mean, doesn't contain any cycle, and also is a spanning tree, meaning that touches all the vertices. How did I find this tree? Well, you saw that I was doing more or less randomly, just having in mind that have to be a tree and have to span all the vertices. But imagine that when you have many vertices here, it may be complicated to find a spanning tree. And there are many algorithms that are going to allow us to actually find a spanning tree. Well, we are going to see an algorithm to find a spanning tree. I mean, you can find it by hand, as I just did before, or when the graph becomes complicated, especially with a lot of nodes, we're going to need algorithm to actually search for a spanning tree. So this is the algorithm that we are going to see. It's called the breadth first search algorithm. Let's see if we understand all the steps. The step one, we have to find choose a random vertex. So any one. So for instance, here I'm going to choose this one. So you choose any vertex you like of your graph. And so this is what I'm going to call my root. After that, you situate yourself here at your root, and the second step says travel all the edges incident with a root vertex. Remember, incident means all the ones that share this extreme here, right? So in this case will be these two. So we take then we add these two edges. And so in the step 3, it says give an order to this set of new vertices added. So the new set of vertices is this one and this one. I'm going to give an order. In this case, the nodes have numbers. Let's use just the numerical order here, the increasing order of number, 3, 5. So 3 will be first, 5 will be second. You just have to give an order, whatever order you like to these new vertices. In this case, I'm going to say this is first and this is second. And then in the step 4, we are asked to consider each of these vertices in order. I'm going to start with this one and treat it as you treat the first root. Consider all the adjacent, all the incident edges, but with a condition that do not produce a cycle. So, and they are also unvisited. So there are many conditions here. So first, you will check all the ones that are incident. Of those, check which ones are unvisited. You didn't visit yet. And also check that the ones that you are choosing do not produce a cycle. So I situate myself now in the first one. Remember, there is an order between 3 and 5. The first one is 3. I situate myself there, and I look at all the incident ones. Will be this, and this. Of course, 4 is already visited. That one doesn't count. So I have only this and this. But the 3, 4 will produce a cycle. So that one, I don't choose it either. So the only one that I can choose from 3 is the 3, 6 edge. I choose that one. Okay, I'm done with 3. And now I go to the next one in order. Remember that there was an order between 3 and 5. The next one is 5. And now in 5, I do the same. So see that here we have all these adjacent, all these incident edges at 5. Which one of these are the good ones? Well, the 5, 4, that one I will not choose because this is already visited. So let's see this one. The 5, 3, that one is not a good choice either because will produce a cycle. The 5, 1, that's good. And the 5, 7, that's good. So I consider these two. Okay? But you see that by doing that, so I'm getting now 2 new nodes for my tree, and this other one too. So these are all the nodes that we visit so far. And so in the step 5, so we are told to repeat the method with a new set of vertices. So now we have these blue vertices here, the 1, 7, and 6, and in each of them, we had to put an order. Let's still keep the numerical order. The increasing numerical order, since it doesn't really matter. So we have to put just an arbitrary order here. So the 1 is going to be the first one, the 6 is going to be the second, and the 7 is going to be the third. And so in each one, I'm going to repeat exactly the same. In 1, for instance, what are the incident edges? This and this. Of course, the 1, 5 is already visited, so the only one that I'm going to add is this one. But then, by adding this one, I'm done with all the vertices. You see that I travel already all the vertices. Well, that result then, when all the vertices have been visited, is just the spanning tree. So what we got here, as a result, is a spanning tree. You see, this is a tree, right? Doesn't have all the cycles that have the original graph. So this is a subgraph of this with the conditions that is a tree and is spanning. Well, the spanning tree, this algorithm always gives us a result a spanning tree, though the spanning tree is not unique. You see that there are many choices that we are doing here, starting with choosing the vertex at the beginning to start with. So depending on your choice there, you will have as a output of the algorithm different spanning trees. A very important idea in computer science also is that when you have more than one spanning tree, if this graph was weighted, let's say if each of the vertices here has some weight, you may be interested in, of all the spanning trees, which one is the optimal. That is what is called a minimal spanning tree. A minimal spanning tree is then a spanning tree, as we have seen before, but one of which the addition of the weights in each edge is minimal. So, for instance, in this case, if I start, let's say, with this vertex, I can consider this spanning tree again here, 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 and here. That's a good spanning tree. I mean, it's clearly a tree. I didn't put any cycle. And it's spanning, right? I mean, I'm traveling all the vertices. But is it the minimum? So think for a moment what other. There are many spanning trees that you can calculate here. So this one that I calculate, the weight of this one will be 4 plus 7 plus 2 plus 3 and plus 3. Which is 19, right? So look for other spanning trees in this graph and see if you can find one that has less weight than 19. We will see one algorithm in order to find the minimal spanning tree. So this is a little complicated algorithm, but it's possible to code and get always as an output the minimal spanning tree. Well, the idea of this algorithm that we will see in a moment in a concrete graph, but the idea is to separate somehow the nodes of the vertex into sets. The set of the left and the right, let's say. And these sets are going to be varying in each of the steps of the algorithm. You are going to start at the beginning with a very small set L that is going to be just a random node. You start by calling L one part of the graph, and the rest of the graph will be R. And so in each step, the idea is to be growing L. L is going to be, at the end, your minimal spanning tree. So you are going to start with a vertex in L, and at each step, you are going to be growing your spanning tree. I mean, putting more things in L, taking out things from R. And the way that you put things in one and take out is going to be based in the idea of the path that connect, let's say, two parts of the graph. So, for instance, in this graph, so let's say if the set L were this and the set R will be all the rest R. So the connection between these sets, what we are going to call the cuts, or the connection between the sets, are going to be all the edges that have one extreme in the L and another extreme in R. So, for instance, the connections in this case are going to be this, are going to be this, and are going to be this. These are the edges that are not completely in L and not completely in R. So, of these edges, you will need to choose the cheapest one, I mean, the one that has the minimal number. And then you are going to be doing at each step this idea of taking out nodes from the R part and putting in L with that criterion of choosing always the cheapest edge. And you are going to continue this until all the vertices of the graph are actually in L. When that happens, the set L will be your minimal spanning tree. So we will see now how to work this in instructions in a concrete example. Maybe write down your instructions in a piece of paper, so now when we see the example, you are following all the instructions. So let's consider this graph. This is obviously not a tree, right? So we are going to find the minimal spanning tree here. Starting with the algorithm, we choose arbitrarily any vertex. I choose here the vertex D as my root vertex to start. So that means that my set L is going to start being just that vertex, and the set R will be the rest. So in the first step, we have that these are our sets L and R. And so now, to start passing nodes from R to L, let's observe the edges, the cut edges that we have here, the connecting edges between the two sets. This is the key point of the algorithm. So the connecting edges are going to be this one, this one, this one, and this one. So of these four edges, which one I'm going to choose? What do you think? Well, I will choose the cheapest one. So in this case is this one. Okay, so that's the choice of my tree so far. I start with this one, I choose this, and I have this. This is then my spanning tree so far. So what I'm going to do now is to write down my new sets L and R. So now L, it got all these things in it. So the node A that was in R before now is in L. And in R we have all the rest of the graph, right? So that would be R. And so now we look at what are the cut edges. So are going to be this one, this one, this one, and this one. So of all these edges, which one I'm going to choose? So I will choose the cheapest one. So I will choose this one. So now my new path, my new spanning tree is this one that we have here in red. So observe that the node F that used to be in the right now is in the left. And so I write again what is my new L set. So the L set is going to be this one, and the R is going to be all the rest. And so again, I mark now the cut edges. So this edge, this one, this one, this one, and this one. All these ones are connecting edges. So now, which one I choose? Let's look carefully at all the weights. This is the cheapest one, so that's the one that I'm going to move to L. And so this is the graph that I have so far. Again, I continue to write my set L. Observe now that this edge is completely in the set L, and R is going to be this set here. So now the new connecting edges are going to be this one, this, and this. So the cheapest one of this one is going to be this, so that's the one that I'm going to choose. So this is the spanning tree I have so far. I put again my L that is growing now, so L is this one, and R is this one now. And again, I look at the cut edges. So this one, this one, this one, and this one. So of this one, the cheapest one is this one. That's the one that I'm going to choose. So the vertex C is the one that is going to change places. So now this is my spanning tree so far. So I put again L, that now is really big. So L is going to be all this, and R becomes just this. Again, I look at the connecting edges, that is this and this. The cheapest one is this, that's the one I'm going to choose. And so G is going to pass to L, and I'm done, because now all the vertices belong to the set L, so the set R now is empty. This tree that we see here is the minimal spanning tree. So we can also count, we can also actually add the weights and see how much is the weight of this tree. So we can see that the weight of this tree is actually 39 if I add them correctly. And so you can check all the other possible spanning trees that you may find others, but this is the optimal one.